Good morning, everyone, and welcome to our ESI webinar. Today we'll be discussing how to engineer and manufacture high-quality and cost-efficient electrified vehicles with the best possible range. We will have two presentations, one by Caroline Burrow on the design and engineering of EVs, and one by Harold Posner and Eric Kam on the manufacturing of those vehicles. We'll be discussing the engineering and manufacturing challenges and how virtual prototyping has become a major tool, not only to optimize but also to adjust vehicles and best meet the market's demands. As we all know, one of the main challenges that OEMs are struggling with is the mass adoption of EVs. And to achieve that, they must deliver not only on quality but battery range, performance, and safety of the vehicles, all the while meeting the right cost and time constraints. And these many challenges are affecting the entire product development team, from the design and product engineering to the product integration to the manufacturing planning and the manufacturing as a whole. All these teams have to make the right choices in order to achieve their targets, whether it is finding the right balance between cost and range, or consumer appeal and styling, meeting regulations, delivering the right safety, comfort, ride quality, all the while ensuring on-time delivery, optimal performance, and manufacturability. This is why, through the engineering and manufacturing solutions that we'll be touching today, we will show you how to overcome these challenges and help you reach the required performance and range of fully electric and electrified vehicles. So whatever choices you make, digital tests and virtual prototyping are the key to achieve your targets. At ESI Group, we're leveraging over 40 years of domain and industry-specific expertise to help you achieve these goals. And we're doing this by replacing real tests by virtual tests and prototypes for product development, pre-certification, and for in-service performance, maintenance, and retirement. So I'll let you now get into the details of EV challenges with Caroline Burrow as she discusses the design and engineering challenges and solutions. Thank you.
Good morning, ladies and gentlemen. My name is Caroline Burrow. I am in charge of marketing strategy and business development for engineering solutions. And I propose you to look together during this webinar what ESI proposed to engineering teams. As you all know, the automotive industry is living a revolution linked to new mobility usage. Already existing shared car and mobility usage or Uberization or future usage linked to autonomous car all lead to fully new car concepts, and they represent a very big challenge for the engineer. Today already engineering teams have to find solutions for electric or hybrid vehicle problematics such as range increase, but also new regulation or new expected performances linked to the introduction of batteries. We think of course of crash test, of battery cooling, but also on weight distribution linked to this battery, and also on water protection. Additionally, you have also the problematic of comfort linked to noise or absence of noise. Later, but already under development, you have a problematic of autonomous driving that have to be answered, such as cabin design, energy consumption, sensor management, and of course dedicated new safety issues. So, aeronautic industry is also living a transformation that represents big challenges for engineering team. Here you have mentioned the electric aircraft, but you have also some porosity coming between the ground transportation industry and air transportation. You can see some new flying car concepts arriving on the market. The change impact also the cabin and the cockpit that are evolving to answer both new business model of airline or business jet companies, and also new human-machine interface in the cockpit. Answering all these requests coming through complex and sometimes contradictory requirements, in the same time proposing innovations in a very short time at a controlled cost represents a very big challenge for engineering organization and lead to a necessary transformation in the development of a product. So what ESI propose is solutions of virtual prototyping to support this transformation. Virtual prototypes that are reliable. That means that you could accurately predict the performance of a given design in early phase before design is frozen. Virtual prototypes that are holistic. We could eliminate the need of costly and time-consuming real prototypes that comes too late in the process. Virtual prototypes that have to be efficient so that you can break silos between engineering teams and accelerate interaction to converge faster. And then smart virtual prototype. That means that you could accurately predict the behavior of all components when interacting with system intelligence. So let's present you some of these solutions, starting with ESI's flagship software, ESI Virtual Performance Solution. Lightweight engineering. One of the necessary problematic to be answered, whatever is the type of vehicle. And as there is no magic material, you will have to use and to select the right material at the right place. So that leads to a multi-material usage in car body. Unfortunately, the weak point then is the junction between these different materials. So what we propose is a multi-scale approach. That means that we will locally detail the junction just when it is necessary to be sure we catch up the potential rupture. So that leads to a reliable, predictable product performance. Lightweight engineering means often the introduction of composite. So this is an example through a US car project involving Chrysler, Ford and GM with the objective of 30% weight reduction, putting in the bumper, replacing a bumper in steel by composite. And of course, you need to be able to catch up the performance of composite material too. Here you can see the reversal of weight spiral presented by Volkswagen, showing how an intelligent body material design will lead to a light chassis and then a downsized engine or less battery usage. And to achieve that, you need to select the right material, you need to introduce composite, but you need also to remove any security margin. That means that you need a fully reliable, accurate simulation of your product performance. And the only way is to take into account the way each component has been built, so to take into account the virtual manufacturing of each component inside the assessments of your virtual performance of a car. Here you have a perfect example of a usage of virtual prototyping with this startup, Gazeltep, proposing recently created in 2014 and proposing a fully new concept of car based on lightweight with 10 chassis parts in composite instead of 300. And with a fully new concept also of building this car. And they use and they develop this innovation completely with virtual prototyping without any real prototype, and they explain that each design iteration take them only 1 week instead of 5 months and cost them only 10 kilo euro instead of 1 million euro for a standard car. So this is a very good example how virtual prototyping can support innovation and startup. You have another example of a startup creating in 2012 with Explicit that developed and proposed a fully new aircraft economic glass seat concept done in titanium. So that made them at that time the lightest economic glass seat. And again, they explore their innovative design, their innovative idea without any real prototype. Everything was done virtually, including the pre-certification of this seat. Here, an example, a perfect example of regulation changing, evolving, with some new crash test arriving, and that will impact typically the electrical car. So you need also to make sure that your virtual prototyping is reliable and able to predict such complex new regulation. You need also to test your car in realistic operating conditions and still having a reliable, predictable product performance. Here you have two examples, one regarding the exterior wind noise that can be predicted, but also all related to water. So simulating the water behavior, and especially when a car is crossing water, which is very important for electric car, to check that you have no water intrusion in some battery compartment, and also having the possibility to fully simulate the drivability, the durability of your car in such realistic operating conditions. Acoustic engineering is very important. I talked briefly of that for automotive car, but of course for electric car this is something absolutely needed, because you have no more noise inside the car, so every small noise that were previously hidden by the powertrain, by the engine, is now can be now listened. So there is a big work to be done on the interior noise, and also some big work about the passive safety because of the absence of noise of electric car. For aircraft industry, this is largely used for now long time ago for any type of frequency, and again also for aerospace industry. This is also something that has been completely proven and that is fully used. One of the big challenges, I talked about that at the beginning, is the increase of driving range. And one of the components that consume lots of energy is the cabin. So of course you can increase the battery and so on, but you can also manage better the energy consumption of the cabin without reducing the comfort. And one specific topic is the thermal comfort that need to be optimized regarding the energy consumption of the vehicle. And one way is to balance correctly the HVAC system with the seat heating system or seat ventilated system. And this is what we propose through a smart virtual prototype that is able to link together a digital human model, a virtual prototype of the seat, and the virtual prototype of the cabin, combining the HVAC system, the seat behavior with heating and cooling system, and the human comfort, thermal comfort evaluation. Additionally, you add some system to optimize all this. Smart prototype, this is another example where you can combine 1D through Simulation X with 3D model to have something completely smart, where you can manage the interaction between the component plus a reliable 3D modeling. And if you go at the very beginning of your development process, where you are only at a model-based design, then you can use open source software like Scilab to manage the requirement complexity with model-based design. And this is what is done with Honda, using this at the early stage of the design process. We talked at the beginning about an efficient prototype. This is very important to have a prototype covering all the application, and that will enable a right trade-off to break silos between teams and make sure that around one virtual prototype on which they will be able to test different applications, different problematic, they will be able, the engineering team will be able to take the right decision And this is what is explained by Honda, explaining that they are leveraging the capacity of virtual performance solution single core model on a full car for our latest vehicle platform development. The consistent chaining of virtual manufacturing results and virtual performance, not only for crash and safety domains, but also for NVH and durability, is a definite technological breakthrough. Another example with Skoda, also investigating several options before design was frozen, thanks to a single core model, so one model, one virtual prototype on which several types of tests can be performed virtually. Lamborghini, explaining that they could go from the crash model applicable for body stiffness simulation, going from 1 week to 1 hour. Audi, reusing the crash model for vibration, misuse, and thermal load case, and saving time from 1 month to 1 day. So to conclude, what we propose is a smart virtual prototypes enabling the necessary transformation of engineering process through reliable, holistic, efficient and smart virtual prototype, and that will lead to better trade-off decision before design is frozen up to a model-based system engineering.
Thank you, Caroline. So now we'll move on to Harold Posner, who will be discussing the manufacturing challenges for electric vehicles. Thank you.
Thank you. This part of the talk focuses on manufacturing high-quality and cost-efficient electrified vehicles with the best possible range. The body in white is one prominent object for the exercise to balance design targets and cost per range. On the upper left side, you see a typical compact class reference vehicle with steel body and internal combustion engine. On the right upper side, you see a study of the European Aluminium Association on whether the cost of lightweighting a car with the intensive use of aluminum could be compensated for by a reduction in the cost of the batteries based on the reduction of weight. Below is an ultimate lightweight design made with carbon fiber that is used in the BMW i8. The cost per 1 kilogram weight savings was certainly at the level where a strategic decision was required. For the body in white, a well-designed mixture of aluminum and high-strength steel seems to be a feasible solution at the right cost. With respect to cost per range or cost per miles per gallon and consequent choices of the price point, stamping of metals is the single most efficient choice for the mass production of parts typical for a body in white structure. For a complete vehicle, chassis and exterior account for 35% of total material value. Estimated is a stamped component value of 1,100 euros per vehicle following a study of Roland Berger. In a body in white, three types of components can be distinguished. First, the components with the most end-user experience, exterior Class A panels and doors enclosures. They decide on the perceived quality of the car and display the design intent. Class A surface quality is the main challenge for the forming of Class A panels and doors enclosures. Second, structural components which provide the best possible energy absorption. And third, structural components which provide the ultimate protection of the passenger with a passenger cabin with highest possible strength. Forming to shape with limited elongation and compensational springback are the main manufacturing challenges for structural parts. Class A panels account for most of the cost if it comes to material and tool and die cost. The stamping of those large flimsy panels is in particular delicate since they behave almost like a foil, or as they say on the floor, like a wet noodle. Cracks are more difficult to predict. Next to cracks, surface defects that disturb the perceived quality need to be detected virtually and eliminated. High performance computing paired with accurate modeling allows to secure the stamping of large and flimsy panels to specs. This ultimately protects against unforeseen tryout cost and also helps to minimize the overall tryout cost. Doors enclosures are the customer's first contact with the vehicle, and they become a focus of marketing. In particular, automatic doors enclosures are becoming much more integral to the whole vehicle functionality and styling. Class-leading craftsmanship is required to meet the targets for perceived quality, hand access, efforts, sound quality, impact safety, and noise and water management. With respect to manufacturing, it makes no sense anymore to decouple the stamping of the components of doors and closures from the assembly process. In more recent manufacturing configurations, the assembly starts to be the driver, and stamping and assembly work in team to meet the perceived quality. By changing the traditional way of working, costs can be significantly reduced by avoiding late engineering changes and reworking tools and processes. So how to achieve manufacturability, shape accuracy, and operational excellence? A one-stop job shop from ESI helps you to control and optimize formability, assembly, and perceived quality. Once the parts and doors and closures are done, the body in white is assembled. As an example, take the case of a Model S from Tesla. First, the undercarriage is fabricated. A robot brings front, center, and rear floor panels to the frame. Then a team of robots welds the undercarriage with cold metal transfer welding. Next, a pair of robots installs the completed body sides. Last, a pair of headers is added, which completes the basic structure. To summarize the processes used, the entire body design of the Tesla Model S is joined with cold metal transfer welding, spot welding, structural adhesives, and self-piercing rivets. Cold and hot joining processes produce distortion due to gap closing, mechanical shrinkage effects of cold processes, and the heat effects of thermal processes. Distortion needs to be managed at every assembly step in order to assemble the body in white to specifications. Virtual management of distortion due to the distortion effects of joining processes has a great cost-saving potential because costs due to late engineering changes can be avoided. Sometimes it's even not possible to compensate at the assembly level, and compensation needs to be done at the stamping tool level. If in such case too late discovered, it can result in catastrophic unplanned costs and delays that needs to be avoided under all circumstances. So how to achieve manufacturability, shape accuracy, and operational excellence? A one-stop job shop from ESI helps you to decide where to put joints and clamps and to control and optimize clamping conditions, welding process parameters, joining sequence, and pre-deformation of parts. Looking at carbon fiber car bodies shows that this specific material is well established for high-end vehicles, race cars, and dream cars, which are produced manually in small lots, this almost since 40 years. The well-known Alpha 4C, the Porsche 918 Spyder, and the BMW i8 represent the most recent state-of-the-art. The ultra-lightweight fiber-reinforced plastic materials used are perfectly suited for ultra-lightweight electrified vehicles. However, their usage is often limited to non-structural components. This constraint comes from two main challenges that the automotive industry is trying to overcome, which are cost and production rate. Since the cost of a composite component essentially comes from the material itself, the designer needs to push the envelope of the material capabilities to create maximum optimized designs. That means he or she has to reduce the weight compared to typical aluminum designs for the same purpose by around 25% or more. Just replacing individual metallic parts is not good enough. Instead, a composite structure should perform the function of many metallic parts or assemblies. This means additional functionality should be integrated in the design to make fiber-reinforced designs attractive for mass production. On the manufacturing side, processes are established for ultra-high-strength parts with cycle times of 2 to 3 minutes. The new carbon fiber box of the Chevy Silverado is a sort of hybrid design. It offers a new manufacturing process that is suited to mass production at acceptable costs while providing most advantages of carbon fiber designs. The carbon fiber content is 35% to limit the cost. So how to achieve manufacturability, shape accuracy, and operational excellence? A one-stop job shop from ESI helps you to control and optimize preforming, RTM curing, and distortion compensation. Metal stamping and die casting are two extremely different key manufacturing processes. Die casting is capable of producing parts with extremely complex geometries. It becomes efficient if one cast part can replace several simpler parts. Metal stamping is more economical when it is used for parts with simpler geometries. Stamping is also capable of producing very complex parts, but at a cost. The more complex a part is, the more components the tool and die require. The more tool and die components there are, the higher tooling costs become. If you need to produce a high volume of parts with any level of complexity, die casting is usually the correct choice, and it is more and more used in modern lightweight designs. Manufacturing challenges are the thin wall designs and porosity that must be contained if parts are used for energy absorption. Automotive die casting gains today market shares in the energy absorption discipline since this process is now able to deliver complex parts with the required quality. With the ability to replace several stand parts with one complex cast part and with the right quality, the cost equation becomes right. So how to achieve manufacturability, premium casting quality and operational excellence? A one-stop job shop from ESI helps you to control and optimize the complete filling and solidification process, the choice of the right die casting machine, the piston attributes and deformation and dimensions. Additive manufacturing enables car manufacturers to explore a completely new design space from what traditional processes allowed in the last 20 years. It drives the abilities of die casting processes to manufacture complex parts to the extreme, but at the cost of the ability to produce mass parts, for now. Initially, this process was mainly used in the aeronautics and space industry, where lightweight, which is the main target of electrified vehicles, is one key objective. Nowadays, additive manufacturing becomes more cost-effective, especially for metallic intermediate or finished parts. In 2017, the total investment in new material additive manufacturing printing increased 80% versus 2016, and the automotive industry started to be one of the next industrial sectors that is involved. We are looking forward to seeing totally new designs and applications for complex molds, tools, and components in productions and rapid prototyping. So, whatever choices you make, virtual prototyping from ESI is the key to achieve manufacturability, shape accuracy, class-leading craftsmanships, on-time delivery and operational excellence, and no unforeseen tryout and production cost. Thank you. Next, my colleague Eric is speaking about human-centric aspects of manufacturing. Thank you.
As we can see with the discussion so far, the engineering and design of electrified vehicles is certainly going to change the materials, the architecture, the design, and the layout of modern vehicles. Human-centric product integration and assembly process validation is a way that we are using virtual reality along with the virtual prototype to help people avoid those late engineering changes and issues due to the ergonomics and human factors by allowing them to validate upfront the assembly process as well as service, maintenance, and operation of these new vehicles. Electrical mobility will certainly change the way we design cars. We've been building cars for the last 100+ years with internal combustion engines and typical transmissions. Now, as we think about electrified vehicles and the electrification of those vehicles, we can see that there's a whole new opportunity for the architecture and the use of creative materials and creative lightweighting. However, that does bring about some changes that might not be foreseen in the way that we engineer our vehicles. If we are using novel techniques for the assembly and the order in which we put the cars together, that's certainly going to change the way that we've already proven we know how to build cars. Putting batteries instead of certain frame elements, putting electric engines and motors closer to the point of power distribution so that we don't have a transmission centrally located, but instead hubs and motors at each one of the individual wheels will certainly change the way we have to think about how we assemble and how we produce these vehicles, as well as how we service and support them. By using virtual reality, we can actually experience what it's like to try to assemble and to service these new vehicles. And that's going to mean that we'll have to be able to, in VR, reach in, grab, and assemble and disassemble those vehicle components. And by doing it in VR, we're replicating the experience that we would normally only receive once we're building a practical physical prototype of that vehicle. As we've stated before, using virtual reality or virtual prototyping allows people to reduce the reliance and the requirements for physical and practical prototypes. However, without losing that experience of what it's like to build, assemble, and service those modern vehicles, we have to regain that opportunity for experiencing what it's like to build these cars. And virtual reality, powered by ICIDO, is going to allow us to experience to really, from the first person point of view, put those vehicles together. Additionally, we have the capability to transfer my first person experiences that I might have in virtual reality to a third person analytic body, such as taking the behaviors and the motions that I used in assembling a prototype vehicle in a virtual assembly line. I can also map that behavior to other sizes and other populations of human operators who might be tasked with the requirement of assembling these cars in the factories of the future. This way, I can gain all of the experience that normally only comes from piloting a prototype vehicle by doing a virtual prototype. And that's going to enable us to address all of those human-centric product design as well as assembly process and service process issues that normally would not be recognized until the vehicle was in full production.
Thank you, Eric. Thank you, Harold and Caroline, for great presentations today. I really hope you enjoyed the webinar. We'll be addressing all of your questions via email. And I do want to mention today that we will be attending CES, so if you want to meet with EV specialists from ESI, please reach out to us. We have our website here, and you can just book a meeting, have a demo specifically and dedicated to you. We look forward to meeting you there in Las Vegas from January 8th to January 12th. Have a great day. Thank you.